Good evening. We are Tech Minds, and today we will be presenting key concepts in number theory and demonstrating how they can be implemented in ParaGP, a mathematical software. Well, the purpose of this manual is to cover number theory topics learned during the semester, including divisibility, Euclidean algorithm, Bezout's identity, congruencies, and residue classes. I will also show how to apply these concepts in ParaGP. Let's begin by checking for divisibility. First, let's discuss divisibility. A number is said to divide another number, let's say a number b, if there exists an integer k such that b equals k times a. For example, if a equals 2 and b equals 10 from the expression b equals k times a, we can say that 10 equals k times 2. That is k equals 10 divided by 2, which is 5. This k is an integer 5, making the divisibility correct. Now, let's implement the divisibility. Let's check whether the number b is divisible by 3, where the number b is 200 million. Now, can times a k equals k return 1. This k multiplied 0. Okay. Now we test the function with now we will just now we will test the function with a equals 3 and b equals 200 million. So a equals 3 and b equals 200 million, and then now is divisible a b and so you see we get a divided by b is false because there is no integer k such that b equals k times a. Since a is assigned the value of 3 and b the value of 200 million, the divisibility is false because there is no integer k as stated before. Now we move to criteria for, let's say, as seen before, the criteria for divisibility by 3. So if we let b be an integer and 3 over b, if and only if the sum of the digits, let the sum of the digits of b is divisible by 3 base 10. Example, if we consider the number 3000 3,245,619 determine whether it's divisible by 3. First, we will add the digits of b ignoring the zeros. So it will be 3 plus 2 plus 4 plus 5 plus 6 plus 1 plus 9, giving us 30. Then apply the theorem to check for divisibility of 3. That is 30 divided by 3, we get 10. Conclusion being 3 being the number b is divisible by 3. Now we can implement an implementation of this in PariGP will be, uh, let's say now we have that number to check if it's divisible by 3 through the same. So I will write the function first, then we will test. So sum digits equals, so sum digits equals sum of I equals 1. Sum of 1, it's a comma, get a hashtag string. I okay now if let's say some digits 30, let's say print 3 comma b is divisible is let's say it's true because the sum of its digits equals, then we write now sum digits is divisible by 3. And then we return 0. And then now return 1. Print else. Let's see now for this one it will be false because it's true because okay because sum its digits equals sum of digits comma is not divisible by 3. Okay, so now we return 0. Now, okay. So now we test the function. We have the number b, which equals 3, 4, 5, 6, 7, 2, 8, 9, 3, 2, 1. And now we take it as is divisible by 3. And as you can see, the function converts the number b into a string to sum the digits and check if the sum of the digits is divisible by 3, returning either true 1 or false 0 for identified solution. In this case, it brings true because the sum of its digits equals the sum of its digits, because the sum of its digits is divisible by 3. Okay. Now we move to the criteria for divisibility of 2.
Thank you, Sir Frederick, for that lively presentation of the first divisibilities. And so we are going to check for the divisibility for criteria for the divisibility by 2. And first, we'll begin by the definition. And we understand that let's define b. Let's have b as an integer, and 2 is divisible by b if and only if the last digits of b is either a 0, 2, 4, 6, or even or 8. And what do we mean by that? That is if the last digit of the number is an even number. For example, consider the number b is equals to 91 912456723898. For this case, we see that the last digit of the number is an 8. And so, step 1, we check whether the last digit is an even number or not. And 8 is even. Therefore, the conclusion is 2 is divisible by 912456723898. It's true. This one can be represented practically on the GP. And how do we represent it? Let's take for instance that we have this instance that we want to represent. Determine whether b is divisible by 2, where b is 7658903456278910336. Using the divisibility theorem, Using the divisibility theorem of 2, we can represent this on the GP. And how do we do it? First, we will introduce the function. The function is is divisible by 2. Is divisible by 2, and declare a variable b. And what's the first thing that we are going to do? First, we have to extract the last digit from the number or from the integer b. So what do? We extract the last digit. So last digit is equals to b modulus 10. This is the simplest way of extracting the last digit from the number from the integer b. This is one of the simplest way we can extract the last digit from it. And so after we have extracted the last digit, now we introduce the checking for the divisibility option, and that's where we introduce the if block, and that is if last if last digit if last digit modulus 2 is equals to 0, what do we output? Then we'll print that 2 that 2 divided by 2 divided by b is divisible or we can say is is true because because what? Last because last digit last digit is divisible by 2. And for this case, we return we return 1 for the option. Else, or since we are using if and only if, print 2 divided by b is false because last digit is not divisible by 2. We return a 0. So this is the function that we are using. So for our case, we will define the value of b is equals to, the number is too long, and the number is, let's say for our case we are using the numbers 53, 2, 4, 1, 7, 8, 9. Then we'll print is divisible. We'll call the function by is divisible by 2. Is divisible by 2, and try to output and see what we are going to obtain for this case. So for this case we are obtaining that 2, no, the value of b, which is 53,241,789 is not divisible by 2. This is because the last digit being obtained from the number is 9. And based on how we understood that a number is divisible by 2 if the last digit being obtained is divisible by 2. And so for this instance, the last digit of the number is 9. And so since 9 is not divisible by 2, for this case, we are being we are receiving 0 as the output because it's false. So we have just proven that this number is not divisible by 2. And so we are going to move swiftly back for checking the divisibility for we are going to check for the divisibility of we are going to check for the divisibility of we are going to check for the divisibility by 4. And we'll begin by definition. And for this case, we will have an integer b, and we understand that b is divisible by 4 if and only if the number formed by the last two digits of b is divisible by 4. And so for instance, if we have the number 526 and we want to check if it's divisible by 4, we will only extract the last digit, that is the last two digits, that is 26, and check if 4 is being divisible, if 226 is divisible by 4 and there is no remainder. And so let's consider the example being provided here, that let the number b is equals to 456 and 37, 86, 23, 141, 69, 4. Determine whether b is divisible by 4. So step 1, we check whether the last two digits are divisible by 4. And from the number that has been provided, the last two digits are 90. It's 9 and 4. And so we come to the conclusion that since the last two digits 9 and 4 are not divisible by 4, then the number is not divisible by 4. And so this one can be also represented on in GP, and for this case we can use the divisibility. We can check for the divisibility theorem of any number, of any integer number, that is b can be any integer number, that is either 126, 100 or so. And so for this case I'm going to represent on how we can check for the divisibility of 4 on the GP. And we will be using any example, not the example being provided here. So Let me show you how we implement that on PariGP. So first of all, we begin by defining the function. And so we're going to define the function is divisible, divisible, divisible by 4. That's the function that you're going to define for this case, is divisible by 4. And we'll declare some variable b that is going to be used for this case. And first, we have to extract the last two digits because we had been told that a number is divisible by 4 if and only if the last two digits are divisible by 4. So what do we do first? First, we extract the last two digits from the integer b or from the number b. And so how do we do that? First, we declare the last two digits. Last two digits. And how do we extract them? Is equals to b modulus 100. This is the simplest way of extracting the last two digits from a number. You just write the number and modulus 100. And so after after extracting the last two digits, then what do we do next? We introduce the if block, and the if block will be used to check for the divisibility. And so for this case, it will be if last two last two two digits if last two digits modulus 4 is equals to 0, then what? If last two digits modulus 4 is equals to 0, then what are we going to output? Then print, that is, we print 4 4 4 modulus 4 is divided by b is true because last two digits, the ones that we had extracted at the beginning, last two digits is divisible by 4. So for this case, you return the value to be 0. So that's how we test for the divisibility of 4. And we have been we have determined how we have seen how that's being done. Yeah, so that's how we do for the divisibility of 4. And so since we have already understood how we utilized the concept on PariGP, let's move also and check for the divisibility of the criteria for the divisibility by 5. And we can define that. First, we begin by definition, and there we have an integer b, and b is divisible by 5 if and only if the last digit of b is either a 0 or 5. An example, let's consider the number b as 56, 78, 45, 32, 015, and determine whether 5 is divisible by that number. So step 1, what do? We check whether the last digit of b is either 0 or 5. And so from the conclusion that we had drawn earlier, that if and only if the last digit of b is either 0 or 5, we come to the conclusion that since the last digit is 5, then the number b is divisible by 5. And so that's how we check for the divisibility of 5. That also can be represented on the PariGP using the following code. So you can go through the code and understand it clear. And so we see that for the first value of B, it's evident that the last digit and is 3. And based on the divisibility theorem of 5, the number is not divisible by 5. But for the second value, the last digit is 5, which is qualifies under the divisibility theorem of 5. Thus, the output is 1, which is true that the number is divisible by 5. So swiftly, I'm also moving to check for the criteria for divisibility by 6. And first, what do? We define the number, an integer b, and 6 is divisible by b if and only if b is divisible by 2 and also b is divisible by 3. And so what do we check for this instance? First, we'll check if the number is being divisible by 2 and also check if the number is being divisible by 3. And so let's consider the number b is equals to 56, 78, 45, 32, 01, 51, 13, and determine whether b is divisible by 6. So step 1, we check whether b is divisible by 2 by checking the last digits of the number, which should be an even number for it to be divisible by 2. And the last digit is 3. Since it is 3, the number is not divisible by 2. Just if we can draw back on how we were checking for divisibility by 2, we were determining if the last digit is divisible by 2. And so for this number, we are for this number, we have seen that 3 is not divisible by 2. And so this whole entire process is broken down because the last digit is not divisible by 2. So therefore, we come to the conclusion that since b is not divisible by 2, no need to check for divisibility for 3, and thus b is not divisible by 6. This also can be implemented on the PariGP. And so first we'll begin by checking for the divisibility of 2, then check for the divisibility, then check for the divisibility of 3. And so this is the code that can be used to. So this is the code that can be utilized to check for the divisibility. And so you can just use this code and check for the divisibility of 6. Next, we are going to check for the divisibility by 7. And first, we'll have to define an integer b. And b is divisible by 7 if and only if the number x minus 2y is divisible by 7, where y is the last digit in B and X is obtained by B by deleting its last digit. Example, consider the number B is equals to 56,784. Determine whether 7 whether B is divisible by 7. So step 1, we identify the last digit 4 and remove the number from the integer value. That is y is equals to 4 and x is equals to 5678, and x minus 2y is equals to 5670. So step 2, we repeat the step 1 until the smallest digit is obtained. Step 3, the final integer after this process is 42, which is divisible by 7. Thus the integer b is divisible by 7. And so that's how we check for the divisibility of 7. And this one also can be represented on the PariGP, where b will have it as 14 or b will have it as 7, or we can have the value of b as 2,780,190 using the divisibility theorem of 7. And so this is the code that can be used to check for the divisibility on PariGP. And so we'll have to identify a function 7 and commit, and then we will check for the divisibility. First we have to extract the last digit, then after extracting we also work on the remaining number. So you can use this code to extract and find divisibility of 7. So next we are going to check for the divisibility by 8. And so we'll have an integer b as an integer, and then we'll check that if and only if the number formed by the last three digits of b is divisible by 8. And so if we consider the number b as 46, 63, 78, 62, 31, 41, 698, we can be able to determine that whether b is divisible by 8. How? Step number 1, we check whether the last digits are divisible by 8. And from the above number, we can extract the last digit as 6994. And the conclusion, what conclusion are we coming to? That since the last three digits 694 are not divisible by 8, then the number is not divisible by 8. This also can be represented on the PariGP, and the implementation on PariGP can be in this manner. First, you have to extract the last digits, and there is a simpler way on how to extract the last digits from there using the PariGP. So you just take the number modulus 1,000. And so this is the code that can be utilized. So you can use this code to extract and find out if the number is divisible by 8 on PariGP. So thank you for that. And we'll move to the division theorem. And I will welcome my second facilitator for today, who is Samuel. No.
Division theorem. Well, division theorem states that for every two integers a and b, where b is not equal to 0, there exist unique integers q, quotient, and r, which is the remainder, such that a equals bq plus r, where 0 is less than is less where r is less or equal to 0, or b. This theorem guarantees that when an integer is divided by another, it results in the quotient and the remainder, which is unique for given values of A and B. Example, we have an example. Let A equals 23 and B equals 7. Quotient Q, the largest integer, times B that does not exist does not exceed A. The remainder R, the difference which is the difference between A and BQ since 7 times 3 plus 2 equals 23, we have Q, the quotient, which is 3, and R, the remainder, which is 2. Now, the implementation in PariGP will be well. It's me. The implementation will be in PariGP will be let's as seen. First, we will set the parity size and now then we will define the two integers. A equals 23, B equals 7, and then now we compute the quotient and the remainder, which the quotient will be A divided by B, the integer division, and the remainder will be A modulus B. And then now we print the quotient and the remainder. In this case, the quotient is 3 and the remainder is 2. Now, let's let's move to the Euclidean algorithm. This is an efficient method for computing the GCD of two integers. The Euclidean algorithm works by replacing the number with, with its remainder when divided by the smaller number until the remainder it becomes 0. Now, the steps for this algorithm are four, and they are very simple. So, let's say we have two numbers, A and B, where let's say A is greater than B, and now we compute which is R. R will be A modulus B, and then now we replace A with B and B with R, and then we repeat the process until B is becomes 0, and the last non-zero remainder is the GCD of A and B. For example, we have two numbers 48 and 18. So GCD, or the modulus for 48 and 18, is 12. And now we replace 48 and 18 with 18 and 12. Like we said, replace A with B and B with R. And now it becomes 8 modulus 12, which is 6. And now we replace A with B and B with R. It becomes 12 mod 6. 12 mod 6 becomes 0, which now becomes the GCD. Now the last non-zero remainder is 6. So the GCD for 48 and 18 is 6. And the implementation in PariGP will be just simply just like just GCD was. But if we want to implement it manually, we will have, you can see, let me zoom here. We will have Euclidean AB while B equals AB, well B AB equals B A modulus B, and it will return A. And now we will now you test it with Euclidean 4818, you get 6 still. Now we move to Bezout's identity. Let's go step by step first. To compute Bezout coefficients, let's say for A, we say 48A equals 48, and B, it will be 18B for 18. And then now we will using the extended Euclidean algorithm. Let's now move to the steps. Step one will be to compute the GCD. We will still use the previous example for 48 and 18 using the Euclidean algorithm. We apply the division algorithm iteratively. Let's say for example, we have 48 divided by 18, which is 248. And now we will divide that by 18. Yes, now remainder 2. So we'll have 48 equals 18 times 2 plus 1248, which is equals to 18 times divided by times 2 plus 12. Now, since the remainder is 0, we conclude that GCD of 48 over 18 equals 0, equals 6. Sorry. Step 2 is to reverse the steps to find x and y. We now express 6 of as a linear combination of 48 and 18. From step 2, we get 6 equals to 18 minus 1 times 126, which is the same as 18 minus 1 times 12. From step 1, substituting 12 equals times this, we can get that we can get the equation x equals negative 1x minus, we can get the solution, the valid solution x equals negative 1x equals negative 1, and y equals 3y equals 3. To verify the solution, we can put it to the test. We can have this math. We can say 48 in brackets negative 1. Let me zoom it for you. We can have this. Now, implementing this in PariGP, when you put all this when you do the math, well, it brings 6, the GCD for 48 and 18. Using PariGP, we can also confirm using Bezut 48, 18, you get negative 1, 3, 6. 6 being the GCD, indicating the the coefficients x and y, and the GCD 6. Now let's move to congruences. By definition, congruence is an equation of the form ax equal is b mod b in brackets mod m. This means that ax minus b is a multiple of m. An example, we can solve 9x mod 26 using modular division. The solution x 17 mod 26. The implementation of linear congruence in PariGP will be solve congruence ABM given with x mod BM over A. Print solution for x mod M. Now we call the function again solve congruence N2126, and it gives the solution x mod 1126 mod 26. Now let me pass it to the next person.
Okay, so the next the next thing you're going to talk about is residue classes. We'll start with the definition, whereby the residue class of an integer a modulo m is the set of all integers that are congruent to a modulo m. So we'll show that using the example, and yeah, so the residue classes modulo 5 are, this is the list for the residue classes, which is 0 for the first class, 0, 5, 10, 15, and it continues. Then there's 1, 6, 11, 16. Then for the third class, it's 2, 7, 12, 17. For the fourth, 3, 8, 13, 18. And for the last one is 4, 5, 4, 9, 14, and 19. So on the implementation in PariGP, so to list all the residue classes modulo M, we're going to initialize M to be 5. Then you're going to write this loop here, whereby for A equals 0, M minus 1, you print the residue class and modulo a m. So this code will print all the residue classes for modulo 5. And so let me scroll down. So to check if the two numbers belong to the same residue classes modulo m, we're going to use this code here. Same residue class, which is our function, a bm equals return a modulo m is equal to b modulo m. So this code here will be used to check whether the two numbers belong to the same residue class modulo m, where in our case it's 5. So that's what we have on residue classes. Then the final task where we are given was on how to use affine cipher to encrypt and decrypt the name of the group, where in our case our group name is TechMinds. So first of all, we're going to start with the encryption process. So the affine cipher encryption formula, we use this expression where e of x equals to 9x plus 21 modulo 26, where x is the plain text letter numerical value, such like a equals to 0, b will be 1, that will continue like that until z, which will be 25. Then 9 is the multiplicative key, which is coprime with 26, and 21 is the additive key, which is also the shift value. So the plain text in our case is statements, which will convert to numbers, and t, its numerical value will be 19, e, its numerical value will be 4, c, its numerical value will be 2, h, the numerical value will be 7, m, its numerical value will be 12, I will be 8, n 13, d 3, and s 18. So we have this table here which we'll use to do the encryption process. So we're going in the first row, we have the plain text, then we have x, then we have the expression 9x plus 21, then modulo 26, then the cipher text. So for t, whose numerical value is 19, when we when we multiply 19 by 9, it will give us 171. Then we add the shift value, which is 21, or the additive key, and the final value will become 192. So 192 modulo 26 is 10, and 10 in the its numerical value represents k. So the ciphertext becomes k. Then e, the same process. E's numerical value is 4. So when you multiply 4 by 9, we get 36. Plus the additive key 21, we get 57. 57 modulo 26, that gives us 5, whose value is equal to f as the ciphertext. And C, numerical value is 2, multiplied by 9, 18 plus 21, 39. 39 modulo 26 gives us 13, whose value is equal to the end letter. So that's the ciphertext. H, numerical value 7, multiplied by 9, 63 plus 21, 84. 84 modulo 26 equals to 6, whose value, whose alphabetical letter is G. Then there's M, 12, 12 times 9 plus 21, 129. 129 modulo 26 equals to 25, whose which stands for the letter Z. And I, alphanumerical value is I, is 8. 8 times 9, 72 plus 21, 93. 93 modulo 26 equals to 15. And 15 stands for P. And the same, 13. 13 times 9, that's 117 plus 21 equals to 138. 138 modulo 26 is 8, which stands for H in the alphabet. Then there's D. Numerical value is 3. 27, which you get by multiplying 9 times 3, so 27 plus 21, get 48. 48 modulo 26 we get 22. 22 stands for W. It's the numerical value for W. So then there is the final one, which is S, and its numerical value is 18. 18 times 9, 162 plus 21 equals 183. 183 modulo 26 is 1, which is the numerical value for B. So the encrypted text check mines will be equal to the, oh sorry, uh, okay, so encrypted text for check mines will be KFN GZPHWB. So that's the encryption part. Then the decryption process is just the reverse. So we're going to use this expression d of y equals to a the power of negative 1 to bracket y minus 21 modulo 26, whereby y is the ciphertext letter, its numerical value. A, the power of negative 1 is the modular inverse of 9 modulo 26, which is 3, and 21 is the additive key, same as in encryption. So our ciphertext is this one, the one which you got above on the encryption process. So we convert it into their numerical values, where k was n, f was 5, n was 13, g was 6, z was 25, p was 15, h was 8, w was 22, b was 1. So we're going to have the same table, but this time on reverse. And so the ciphertext k, numerical value was 10, y minus 21, 10 minus 21 is negative 11. Then 33, so we do the inverse. We said that uh, a negative 1 is the modulo of inverse 9 modulus 26, which is 3. So the negative inverse of 9 modulo inverse of 9 is 3. So that's where we get the negative 33, because we multiply the negative 11 times the 3, which gives us that negative 33. So negative 33 modulo 26 equals to 19. 19 is the numerical value for T on plain text. So we get that, the first one. Then F, the same process. We take Y, its numerical value is 5. So 5, so 5, so 5 negative 5 minus 21 equals to negative 16. Negative 16. So negative 16 we multiply by the modulo inverse of 9, which is 3. It gives us negative 48. Modulo 26, we get the value of 4. So, yeah, sorry about that. So negative 48 modulo 26 equals to 4. And 4 is the numerical value for the letter E. So we go to the next one, which is N. N's numerical value is 13. 13 minus 21 equals to negative 8. And when you multiply it with the modular inverse of 9, which is 3, it gets negative 24. And negative 24 modulo 26 gives us 2. So 2 is the numerical value for the letter C. Then for G, our next letter, its numerical value is 6, as shown above here. Then 6 minus 21 equals to negative 15. Negative 15 multiplied by the modular inverse of 9, which is 3, we get negative 45. And negative 45 modulo 26 is 7, which is the numerical value equal to the letter H, which represents the letter H. So Z the same, 25 minus 21, we get 4. 4 times 3, 12. 12 modulo 26, we get 12, which is the numerical value for M. P the same, 15. 15 minus 21 equals to negative 6 times 3, negative 18. Negative 18 modulo 26 equals to 8, which is the numerical value for I. 8, 8, 8 minus 21, negative 13 times 3, negative 39, and negative 39 modulo 26 is 13. It's positive 13, so which is the numerical value for M. W, its numerical value is 22. 22 minus 21, we get 1. 1 times 3, 3. 3 modulo 26, we get 3. And it's the numerical value for D. Then the last one is B, whose numerical value is 1. 1 minus 21 equals to negative 20. Negative 20 times 3, which is the modular inverse of 9, we get negative 60 modulo 26, and whose value is equals to 18, and 18 is the numerical value for S in the alphabet. So the decrypted text from KFN GZPHWB comes back to tech mines, which was our initial plain text. So yeah, and I guess that's the end of our presentation. Thank you for your time and have a lovely day.